this opportunity for for present my talk. This is actually a scenery of Santiago, but without smoke. Yeah, just when it rains. Some people might not believe that, but this is actually the financial center of Santiago. And here on the back we see the mountains, the Andes, right? So what I want to present today is actually a many-body interacting system, which is in line with what the previous speaker talked. Is a mixture of particles, but in this case we have bosonic particles. We have two species of particles we call A and B, and these species coexist in a ring. So we have an optical lattice which has a ring. And what is interesting is in this problem is that if we combine, if we play, for instance, with the intraspecies, the interspecies interaction, together with the presence of synthetic magnetic field, it's possible to generate a special state. And this special state has the property that can not only be in maximal entangled state, but they also belong to a very special class of states, which is actually a pair-superfluidity phase. And it can also, I can show you that it can also be regarded as a non-thermal state. So this is actually, so this is actually a series of work that has been done in collaboration with several members of our institute. So you can see that there is a synergy here from several top fields. For instance, Sebastián Reyes is an expert in solid-state physics. Miguel Orza, who is a senior professor in our institute, he is an expert in quantum information. Eduard Areva, who is is working photonic lattice, and Dominique Spener is our external collaborator. He's from Grenoble. He's an expert in quantum information. So the outline of my talk is the following. So I will give the original motivation of what inspired us to study this kind of systems, and then I'm going to introduce the model. So I'm going to say a few things about the details of the model. Then later on, I'm going to show you some results. So this was basically the first result that we found. So we were interested in studying the correlation between the currents of particles moving in a ring with the formation of entanglement in the system. And later on, I go to the main result of our talk, is basically how can we create maximal entangled state. It turns out that these maximal entangled states are not also entangled states, but they also belong to this special class of pair-superfluidity states. And if I have time, by the end of the talk, I will give you a very exciting result that some preliminary result that we have about scaling of the entanglement as a function of some of the observables in the system, which is usually the common observable is the momentum distribution of the lattice. So this is basically our main motivation. So we started this project a long time ago. So when you stir up a glass of honey and milk, the first thing that comes to your mind is, what is the miscibility, right? So when they get mixed, and this has been addressed by several experimental groups. So since we have here many interactions, so we have intra and also interspecies interaction, we can have many quantum phases, right? So this is actually in the quantum realm. Oh, sorry, what? So there was a cascade. So, but the main question that we actually want to address is, what can we say about the entanglement between these two subsystems, right? So this is actually what we plan to study. So the model is the following. So we consider two species, and here we have the Hamiltonian for these two species. So this is the kinetic part for the species A and B, plus the interacting part. And by the interacting part, we have repulsive intraspecies interaction, but also we have interspecies interaction. We consider for this moment attractive interaction. And the intriguing part of this Hamiltonian is that the kinetic part. When you can see that the hopping, I mean this is a complex term, so that means this actually belongs to a very hot topic that has been going on during the last years. It belongs to the study of what is called synthetic magnetic fields. Basically, the main motivation for study this kind of system where you have this pair phase is because they want to mimic the system of fractional quantum Hall effects in this kind of cold atoms in optical lattice. So basically, if you forget about this interacting part, you are left with this Hubbard Hamiltonian, and if you suppose you extend it to the 2D lattice, it will be the similar Hamiltonian that you use to describe the motion of electrons in a 2D lattice in the presence of magnetic fields. Of course, here we are talking about neutral atoms, so these basically phases are optically induced. There are several proposals, but the proposal that I like most is basically that one where the people just check the lattice, mimicking the presence of a time periodic driving that breaks the time reversal symmetry. And it turns out that if you go to the high frequency limit, then you get an effective Hamiltonian that is basically this one, where this pair phase is connected to this parameter that breaks the time reversal symmetry in the time periodic driving. So this is I like this proposal because in principle you can continuously vary these parameters. So this allows to do many things, to do many physics. Okay, so now the next question is, okay, we want to find out what is a relevant or observable that can tell you what is the degree of entanglement between these two subspecies. And one could be the current in the system. So suppose we have the original Hamiltonian, we forget about the intraspecies, we only consider the interspecies. So we have this pair phase, and this pair phase break the time reversal symmetry, so we have a current in the system. So the question is, what happened to the current when we turn on the interaction? This is actually the main question here. So we have this, this is the amplitude of the interspecies interaction, and the question is, so what happened to the current on the system? Are they correlated or not? Okay, I go to this point. I'm going to explain all the concepts because I know that there are people here who are not from the community of quantum information. So let's go to first of all, let's define the current of the system. So since we are dealing with the composite system, it's basically the sum of the current of the two species, right? And basically, this is the definition of the current. So it's basically the subtraction of the flux when the particle hop from left to right minus the flux of particle from right to left. But the definition of quantum entanglement is, here we use the word called bipartite entanglement. So we have two subspecies, and for that we use what is called the Schmidt decomposition. Basically, this is a composite state, right? And in order to get information about the entanglement, we actually go to the diagonal basis. So in the diagonal basis, when you have the vectors for the component A and the component B are the same, if you look carefully here, if for instance this is 1 and the rest are 0, this is a separable state. If at least 2 are different from 0, then you have entangled state. If all of them are the same, then you are in the presence of maximal entangled state. Usually, this is between 0 and 1. And if you look carefully here, these are small values, but all of them are the same, then you get a very highly entangled state. If one is, for those who are familiar with, for instance, with nonlinear physics, this looks pretty similar to what is called a participation number, an inverse of participation numbers. Okay? So this is the quantity that we use. This is called a Schmidt number. This goes from 1 to the dimension, the lowest dimension of one of these Hilbert space of the subsystems. So in order to compare with the current in the system, it is convenient to normalize the quantity such that for this K calligraphy, basically when you have 0, then you have no entanglement, and when you have 1, then you have maximal entanglement. Right? This is it. Okay, so we are talking about a Hamiltonian system. So we are dealing with pure states. Okay, so if you are dealing with mixed states, then probably you need another quantity to characterize the degree of entanglement. JD could be A or B. You know, this applies to to both species. This is the same expression, but D could be A or B. Right? So this is a... So now we come to the point that we want to compare the current and entanglement. And we did for only a few particles, so this is actually a few degrees of freedom. So here we have here, in principle, we have only we consider the trimer, where you have three only lattice sites. And we are, in the first picture here, we have one particle for A and one particle for B. And if you turn on interaction and you let the ball of the system, you see that the patterns are very similar. It's not. So here you see that. So the one is entanglement, and the other quantity is, if you look carefully, is 1 minus, this is the dynamical current versus the initial current in the system before I switch it on the interaction. So eventually the current goes down, but it could go again, restore the current. And this quantity, if the current is suppressed, then you will get the maximum value. Well, it turns out that when you compare these two quantities, what is amazing is that the point where the system reaches the maximum entangled state, you have vanishing current. So we were puzzled by that. We have to, and we did that for only for 2, 1, and then we also increased the number of particles. Here we consider 12 and 3 particles. Still, if you see, if you compare both quantity, you see I will say a good agreement between the two quantities. For instance, if the hopping is very small, then the agreement becomes even better. So this is actually for the absence of the current, and this is the entanglement. But this is actually was the initial part of the work. So we were basically interested in the study of the correlation between these two quantities, but we were not pleased with the fact that we could not explain why the entanglement, the maximum entangled state, is reached at this point where you have vanishing current. We couldn't explain that at that point. So, yes?
Sorry, I probably missed this, but how are you actually computing this time dependence? Is this time dependent DMRG?
No. We are dealing with okay, we are just talking about exact diagonalization. Because we are dealing with only a few particles in the system, we can do that exact diagonalization. There's no problem with that. So that's why we are limited in the number of lattice sites and also the number of particles. So the next question is, okay, we want to create this maximal entangled state, but we want actually the maximal entangled state, but in the spectrum of the energy. So how can we do that? Because here we can only see dynamically, right? After some time, you see this dynamically. And the equation, okay, we can do so, but in that case, we consider the full Hamiltonian. So we consider also the intraspecies interaction and the interspecies interaction, attractive interspecies interaction. And here again, we have the kinetic part. So let's consider the case where you have no hopping. So in that case, one can show that the ground state of the system is given by this Fock state representation, where exactly on the same location you have the same number of particles for E and B. Of course, you can permute the number of particles, but then you will have the same energy. So that means that this state is actually not a single state, but a highly degenerate state. Highly degenerate state. And if you plug here in the Hamiltonian for the interacting part, you will get a prefactor times the sum over the number of particles in each lattice site to the square. But of course, if we set this prefactor to 0, then we get this relation where basically 2b is equal the sum of the intraspecies strain. Then the interaction energy becomes 0. So you can control this. Now the question is, what happens in the case where you have J different from 0? So you will expect a lift of the degeneracy. That is what is expected. But we also know that the two part of the Hamiltonian, the kinetic and interaction part, do not commute. So they don't have a common angle basis. So when we do the simulation, I mean the diagonalization, and we plot the spectrum, we see that if we look carefully in the energy, there are some states which belong, they still have the energy 0. So these states, they are common eigenstate of the two operators in a subspace where the energy is 0. Actually, we were surprised by that, but we became aware that there were some Israeli mathematicians that formulated a theorem saying the same thing about two matrices. So it's possible to have two matrices that in general do not commute, but it is possible to find a common eigenstate, a subspace with a common eigenstate with energy 0. And it turns out that this takes place for a particular pair phase. So this is, well, here we consider the same pair phase for both species. So this is actually was a surprise to us. But if you look carefully, for instance, when you detach J from 0, basically the lowest energy band you can write down in this diagonal basis, where you have this coefficient. And having this coefficient allows you to compute the Schmidt number. So automatically you have the degree of entanglement of the system. So it turns out that these states are not common eigenstate of these two operators, but they also are maximal entangled state. That means that all the coefficients here, the module of these coefficients, are the same. So this was very nice because now we know that this state is actually an eigenstate of this operator with eigenenergy 0. And from this condition also, the fact that you have a periodic boundary condition, then you can find a condition for the phases. So these phases are actually, it gives you a family of the maximal entangled states for the pair phase for the case A and B. And here are plotted this family. So these straight lines correspond to those families. So for different value of M, which is M is an integer, you have a family of these. And this is a reminiscent what you have, for instance, in the fractional quantum Hall effects, that you have a discrete number of states. Right? So, and these red points actually correspond to those red points that are plotted over here. Right? So the next question is what happened with the current? Then we come again to the same point, and we plotted the current. And it turns out that when here UA is equal UB, we consider this case, along the diagonal, which is correspond to the maximal entangled state, you get exactly, you see the maximal entangled value. But the current is the same. So the absence of the current, that means that along the diagonal, you have suppression of the current in the system. So again, we have the same result. We get the same result. So it means that there is a connection between the suppression of the current and the fact that you have maximum entanglement in the system. So what is it? So now we know that these states, they have no current. So are they Mott insulator? They are not, cannot be a Mott insulator state because they are highly coherent state. So what they are, we don't know. But we use it. I remind you that we have intraspecies interaction and also interspecies interaction. When these two interactions reach a balance, in the literature it's possible to find that you have a pair-superfluid phase. So maybe this is connected to the pair-superfluid phase. And then we study now a new observable, which is the standard observable for cold atom physics, is the Momento Distribution. Here is a seminal paper by Greiner and co-authors. So they study basically this transition from a superfluid to Mott insulator. And for the superfluid phase, basically you have a phase coherence in the system. Since you have a phase, when you release the atoms, basically you get in the in the momentum space you get these peaks. So this is an indication that you have interference process. Right? You have a phase coherence, and this is actually an indication that you are in the superfluid case. On the contrary, in the Mott insulator state, all the particles evolve dynamically independent. So the phases can be random, so they don't see each other. And as a result, you don't have phase coherence in the system. So that means that you have, since you don't have interference, you will have a flat distribution like this one. So this means that you can actually determine whether the system is phase coherent or not just by looking at this quantity, which is the called visibility of the system, which is basically the subtraction between the maximum value of the intensity of the Momento distribution pattern, right, minus the minimum. So in this case, you will have 0 value. So let's look at the Momento distribution for our maximal entangled state. So for that, we define it. So the mesh behaves as a multi-insulator state, since there is no current of particle, but at the same time, the mesh is a coherent state. So what is it? So we look at again to this Momento distribution for 2 species, and this is actually for 2 momentum for particles in A, quasi-momentum A, and for B. And we found this nice pattern. So you see that there are straight lines along the anti-diagonal. So if you look at the visibility along this straight line is 0. So it behaves as a multi-insulator. While if you look into the perpendicular direction, it behaves as a perfect superfluid case. But the diagonal case, which is the perpendicular direction, it corresponds to the case where you have both the same velocity. So that means that the particles from A and B, they move with the same velocity. And it turns out that this pattern is actually correspond to the pair-superfluid phase. So pair-superfluid phase, what is it? So this means that there are, first of all, in the pair-superfluid phase, the single order tunneling, that means particles from a single species, they tunnel without telling the other that they are tunneling. And this single order process is suppressed. So we can only have tunneling in pairs through the lattice. So let's see if that is applied to the case where we have a mesh. Let's see we have a mesh. So let's look at the mesh. So here we have our maximal entangled state, which is written in the diagonal basis, right? So if we suppose that we move one particle, right? So that means that we move one particle, so this is not anymore in diagonal basis, so that has to be expanded in the higher energy state, which are orthogonal to the mesh. So if you make a sandwich, for instance, this process is forbidden. As a result, you get that the expectation value for this operator is 0. And that explains why the current vanished. That was the explanation. So, but of course, if the 2 particles tunnel, then you are again in the same representation, and this quantity is different from 0. So that means that you have indeed a current, but the current of a pair of particles. So now we know that these maximal entangled states are not only maximal entangled states, but also pair-superfluid states. So what else? What can we say? So, of course, these are not the ground state of the system, but we know that for instance, when you have the J is relatively small as compared with the intraspecies strain, then all the states which are in the lowest energy band, they share the same property. So in principle, you might think that this state, for instance, the ground state of the system might have a similar property, share the same property as this maximal entangled state. And you compare, for instance, if you compute the second order correlation, this is actually the order parameter for the pair superfluid state. You see that there is a nice correspondence. So when this is actually the spectrum as a function of the pair phase, you see when the system reach higher value of entanglement, also the correlation, this quantity also increase. So there is a correspondence, one-to-one correspondence in this case. So, but of course, you cannot use this in order to characterize the degree of the entanglement of your ground state. You have to use the Momento distribution. And we look at also the momentum distribution for the ground state of the system, and we see that, if you are near to the case where you have a superfluid state, basically you don't have an entangle at all, then basically the system, you see, you have the same peaks that you saw before in the superfluid case. But as long as the entanglement increases, then you see that they start to elongate along the anti-diagonal and they start to squeeze along the diagonal. And you see a very nice agreement with the squeezing and the elongation along the anti-diagonal as you increase the number of, the entanglement increase. So this is actually a nice observable that can be used to characterize entanglement. Right? So the next question is, are there other properties for these special states? So let's talk about what happens if you apply a quantum quench. We know already that these are states where, if you change, for instance, the hopping, then the state will stay invariant. So then you can change everything. So these belong to a special class of states. So this is very relevant when you are in a system out of equilibrium. So we know from basic theory is that when you apply a quench, see, this is the initial state, and this is basically the evolution of the state when H is the new Hamiltonian. It can be written in this way. Automatically, it leads to the case where you have this, expectation value for the observable can be written in this way. In the long time average, this leads to the diagonal case where you have only the diagonal form. All the terms, they cancel out. Right? This is actually. So the question is, what happens in the case where you have a thermalization in the system? So the idea is, well, suppose that we have a quantum mechanical mean value for an observable that behaves thermally. In that case, this long time average, which is written by this, is given by this diagonal term, it can be written as the average of the expectation value in the microcanonical ensemble. Right? So this is basically the expression. So we sum over all the expectation value in all the eigen states which are in the energy shell near the mean energy of the steady state after you apply a quantum quench. But then this implies that, for instance, if suppose that your steady state is basically overlapped with only one eigenstate. Suppose this is one for one eigenstate, and the rest are 0. So that means that this has to be fulfilled. So that means that the expectation value in this eigenstate has to be the same as the computation of the average of the expectation value in the microcanonical ensemble. And this is called the eigenstate thermalization hypothesis. This tells you that these eigenfunctions are thermal states. But the question is our state a thermal state? I would guess no. And actually, there is a recent work has been published very recently where they make a systematic construction of counterexamples to eigenstate thermalization hypothesis. We know there are several examples, for instance, in Maximal and many body localized states, which are not thermal states. But here, the guy proposed the same system, so it's a similar system. So it's the Hamiltonian, where you have this operator, this is a spin system. I don't want to talk about this detail, but the good thing is that they find an eigenstate in the system where you have energy, eigenenergy 0. And they claim this is a non-thermal state. So our model, we also have our mess. And how they prove that? Well, they compute the observable for this hopping, right? And they find that there is a gap with respect to the rest of the eigenstate of the system. So if your system thermalizes, it means that this quantity, for instance, it should fulfill the eigenstate thermalization hypothesis. So this means that the thermodynamic limit should go to 0. But if you include in this sum this non-thermal state, this goes up. If you don't include, this goes down. So that means that you are in the presence of a non-thermal state. And our mess fulfills this condition because this operator over the mesh is 0. And the rest are different from 0. So what time do I have? Still 10 minutes. Oh, okay, I have plenty of time. So let me come to the last point. So we were also looking at this non-equilibrium process, and then we want to predict what is the degree of entanglement before we connect the interaction between the particles. So suppose we have a species of particle in a superfluid and the other in a mode insulator. One is a phase incoherent and the other is coherent. And when you turn interaction, so we know that they are entangled. But how the entanglement scale as a function of one of the observables? We saw already there is a correspondence with the current in the system. But actually, the most standard observable is the visibility. So we actually did that. So we know, for instance, in the momentum distribution for the one particle, this is actually the intensity pattern. You see that if you are a flat distribution, then you are in the mode insulator state. The more difference you have in between the peaks, the more you get closer to the superfluid state. And here, if you plot the visibility as a function of these two relevant quantities, which is a rescaling of the energy of the system, then you get a linear behavior. But then what happened with entanglement with this visibility? So these are preliminary results, but we have also analytical results that confirm our hypothesis. And it turns out that so if you compute entanglement over long time, the system converges to some value. And this value, which is plotted over here, and if you plot it as a function of visibility, scale as a power law with the visibility. So that means that in principle, in your equation, you should get something like, it goes like lambda squared, where lambda is basically this parameter j over u to the square. And we have some analytical result that confirms this result. And so this is something that we are still working on that. And we are very excited about this result because it can tell you good things, how the entanglement is forming these kind of systems. And since you know that how the system, how the entanglement scale with this observable, then you can say a lot of things. So with that, I want to thank for your attention, and I want to acknowledge funding from the SIP project and our university. Thanks a lot.